All right, welcome to the deep dive. Today, we're going deep on cellular automata. You probably know them as CA.
That's right.
And we're going to be looking at, a bunch of different sources on this, including the Stanford Encyclopedia of Philosophy.
Right.
We're going to look at Ilichinsky. We're going to look at Wolfram.
Yeah.
And really, our goal is to kind of explore the philosophical significance of these incredibly simple, rule-based systems.
Yeah.
And see what they tell us about, everything from computation to maybe even the fabric of reality.
You got it. That's what we're going to do. And, from a philosopher's perspective, what's so interesting about cellular automata is that they're discrete and they're abstract computational systems. So what that means is they give us a really clean setting to explore complex phenomena.
Okay. So when we say discrete, what do we mean?
So discrete means that they operate in steps. Each one of the cells that make them up also operate in steps.
Okay.
And the system itself evolves in steps. So it's not like a continuous, flow.
Right. Okay. Gotcha. And then abstract. Why abstract?
Abstract because while we can define them with mathematical precision, they can also be realized in physical systems.
Okay. Got it.
So they're not tied to any particular physical instantiation.
Right.
And they're computational, because, remarkably, they can actually perform computations. So that's the most interesting thing about them.
And that's pretty much, how is that even possible? They seem so simple.
Yeah.
Right.
Well, that's the beauty of it, right? I mean, they're fundamentally different from traditional computers, right?
Right.
Or even, theoretical Turing machines.
Right.
But certain CA, given the right set of rules, have been shown to be capable of actually emulating a universal Turing machine.
Wow, okay.
Which, as you know, is the gold standard for computation.
Right. So it can compute anything that's computable.
That's right, according to the Church-Turing thesis.
Okay, so that is a huge thing. But that's so wild because, here you have these really straightforward rules, but then CA can exhibit this amazingly complex emergent behavior. So, you don't see it in the rules, but somehow these large-scale patterns emerge.
Yeah.
And that has to have huge implications for philosophy, right?
It does.
I mean, metaphysics, epistemology.
Well, especially this idea of emergence,
right?
Which is, at the heart of what cellular automata are all about, which is you have this, macroscopic order arising out of these purely local interactions.
Right.
And, as Epstein said, even perfect knowledge of individual decision rules does not always allow us to predict macroscopic structure. We get macro surprises despite complete micro knowledge.
And that's wild. I mean, think about reductionism.
Exactly. It throws all that into question. Because it gives us a very concrete way to think about it. It's not just an abstract philosophical problem anymore. It's something we can see in action.
Right. And Wolfram, who's really, made huge contributions to this field, he takes this idea of emergence even further, suggesting that CA could maybe be, a lens through which to understand some of philosophy's biggest questions.
Yeah.
And we're talking about stuff like the limits of knowledge, free will, the uniqueness of the human condition, even the foundations of math.
That's right, because what he's saying is that, these simple systems, by looking at how they behave, they might give us new intuitions about how really complex systems, including ourselves and the universe, work.
Okay, so, those are really big claims. But, it really underscores why CA are so important for philosophers. It's one thing to say that, but it gives you something really concrete to think about.
Yeah. So to make this all a bit more concrete, let's look at a classic illustration. The hat rule cellular automata.
Okay, the hat rule. I like that name. It's easy to remember.
Yeah, so imagine a one-dimensional grid of cells, each of which can be in one of two states. Let's just say on or off. On, it's wearing a hat. Off, it's not wearing a hat.
Okay, great. So then what is the hat rule?
So the hat rule is very simple. A cell will be on in the next time step if and only if exactly one of its immediate neighbors was on in the current step.
Okay.
That's it.
So if both neighbors have a hat or neither neighbor have a hat, then the cell in the middle is off.
Exactly.
Okay, got it.
So now let's start with a very simple initial condition.
Okay.
Where only one cell in the middle is on, has a hat, and all the other cells are off.
Okay.
What happens as the system evolves?
I don't know what happens. I mean, it's so simple. Does it just like stay the same?
No, it's not that simple.
Okay.
What happens is you get this surprisingly intricate pattern. It's a triangular pattern that expands over time. It's actually figure 3 in our sources, and you should, if you haven't seen it, it's worth looking at.
Okay.
It's a beautiful example of how you get this profound complexity emerging from something really simple.
Okay, so and that's basically what we're talking about, right?
Yes.
The emergence, like, the rules are so simple. You have the simple initial condition, and then boom, this crazy pattern comes out.
Exactly, because the rule is only local. It only cares about what its immediate neighbors are doing, but somehow from that, you get this global pattern that's not at all obvious from just looking at the rule.
So again, I mean, which is why CA are so exciting for philosophers, because you have this stripped down, idealized way to look at how complexity can come out of simplicity.
Yeah.
And it's not just hand waving, it's math.
Exactly.
Okay. So drawing on our source material, specifically the Stanford Encyclopedia of Philosophy on Cellular Automata, they talk about Andrew Ilikinski's work.
Yeah.
And he kind of breaks down the capabilities of CA into 4 main areas, which I think, are perfect for our discussion today.
Yeah, these are really important areas. So the first one, we call it CA1, highlights cellular automata as these powerful computational engines, right? They're parallel, they're distributed, and really the evolution of the states of the cells can be directly interpreted as a form of computation.
Okay.
So this leads us to compare them with the standard model of computation, which is the Turing machine.
Right.
And that leads to some really interesting questions about the nature of computation itself. Like, what are the limits of computation?
Right. Okay. So we're already getting into philosophy of mind here, which is great.
Great.
Okay, so what's the next one?
The next one is CA2.
Okay.
And this is where we see CA being used to simulate a whole bunch of really interesting phenomena. We're talking about urban growth, the behavior of magnetic materials, neural networks, fluid dynamics, even things like security protocols and bioinformatics.
Wow. So, I mean, these are all very different things. How can one, set of ideas be applied to all of them?
Well, because at the heart of it, these phenomena, they all involve interactions between many simple elements.
Okay.
Right. And CA are really good at modeling that kind of thing.
Okay, so it's like a universal model in a way.
Yeah, I mean they're not a perfect model for everything, but they can capture a lot of the essential features of these complex systems.
Right.
Okay.
And I know that there are some CA that can simulate or model, I should say, continuous systems.
Yeah, so like for example, you can model turbulence using CA.
Okay.
And what's interesting there is that, turbulence is usually described by these continuous equations, right?
Right.
But we can get really good approximations using these discrete CA.
So does that mean that maybe the world is discrete and we just don't know it yet?
Well, that's a question that we're going to come back to later.
Okay. All right. Okay, so what's the next area?
The next one is CA3. And this is where we get really philosophical.
All right, let's get philosophical.
This is CA as conceptual vehicles for studying pattern formation and complexity.
Okay.
So philosophers like Daniel Dennett, for example, he's used Conway's Game of Life, which we'll talk about in more detail later.
Okay.
But he's used it to talk about determinism and also about how these high-level concepts, meaningful concepts, can emerge from really simple underlying rules.
Right. Okay.
So it's a really great example of how CA can be used to think about these really fundamental philosophical issues.
Okay, so I mean, I love that, we can use these really simple systems to think about these really big questions. Okay, so what's the final area?
The final one is CA4.
Okay.
And this is perhaps the most speculative.
All right, I like speculative.
But also potentially the most philosophically rich, which is CA as models of fundamental physics.
Okay, hold on. So we're talking about using CA, these little, computer programs, to model, like, the entire universe.
That's right. So some researchers are proposing that CA could be, discrete counterparts to our current theories in physics, like quantum field theory.
Wow.
And Edward Fredkin, for example, has this hypothesis called the finite nature hypothesis, which suggests that the universe itself might be a giant digital automaton.
So, like, the universe is a computer.
Well, it's more nuanced than that, but that's the basic idea.
Okay, I I can't even wrap my head around that. It's huge.
It is.
But I do see how, like, that would have enormous implications for everything we think we know.
It does. It has implications for physics, metaphysics, epistemology, even the philosophy of information.
All right. Okay. So those are the 4 areas. I think before we jump into those areas, I think it would be good to give a little bit of the history of CA, right?
Yeah, absolutely.
So where do these things even come from?
Well, the father of cellular automata is widely considered to be John von Neumann, and he was working back in the 1950s on this idea of self-replication. He was trying to understand, biological development.
Okay.
And he was, thinking about how you could have a very simple system that could, reproduce itself.
Okay, so like a minimal model of life.
Exactly. And, it's interesting because biological processes seem continuous, right?
Right.
But he chose to focus on a discrete system, a two-dimensional system.
Yeah.
And he came up with this automaton, which was quite complex. It had 29 states.
Wow.
And, these very intricate rules. But it worked.
It could actually reproduce itself.
It could. It was the first formally proven example of a discrete parallel computational model that could, in principle, compute anything.
Okay, so it was a universal computer.
Exactly.
Wow. Okay.
So that was a huge breakthrough.
Yeah. So what happened after von Neumann?
Well, in the early 1960s, E.F. Moore and Myhill came up with something called the Garden of Eden theorems.
Garden of Eden theorem.
Which describes specific patterns that can only exist as initial conditions in a CA. They can never arise from the evolution of other patterns.
Interesting. Okay.
Gustav Hedlund also did some important work on the theory of CA, connecting them to symbolic dynamics.
Okay.
But I think the most famous and maybe the simplest universal computer ever conceived is John Conway's Game of Life.
Right? Okay.
Which was invented in 1970.
Okay.
And, this is a two-dimensional CA, very simple, 2 states per cell.
Okay.
And a very concise set of rules about, how cells are born, how they survive, and how they die.
Right, right.
But it captured the imagination of a lot of people, and it's still being studied today.
Yeah, and a lot of really interesting patterns come out of that, right?
Oh, yeah, we'll talk about that in more detail later.
Okay, cool. And then who else? Who else is doing stuff?
Well, Tommaso Toffoli in 1977 started using CA to directly model physical laws.
Okay.
And he laid the groundwork for studying reversible CA.
Reversible.
Yeah.
Okay, so like you can run it backwards.
Exactly. So you can, you can go back in time, so to speak.
Okay.
And this is interesting because a lot of the fundamental laws of physics are reversible at the microscopic level.
Right. Okay.
So you can think of these CA as maybe capturing something fundamental about physics.
Okay. So we're getting into that CA4 territory now.
Exactly.
Oh.
And then finally, in the 1980s, Stephen Wolfram did a lot of work exploring one-dimensional CA.
Oh.
And he developed a classification scheme for the different types of behavior that you can get.
Right.
And he also, he was very interested in this idea of universal computation in CA.
Okay.
And he conjectured that a particular rule, Rule 110, was capable of universal computation.
Okay.
And this was later proven by Matthew Cook in 2004.
Wow. Okay. So we've got a lot of history here, a lot of really big names, a lot of really interesting ideas.
Yeah, so CA are not just, a fad, they have this very long intellectual history.
Right. Okay. So just to recap the really basic stuff before we jump into the philosophy.
Mm-hmm.
We're talking about these systems, these discrete cells arranged in a lattice.
Right.
And each cell can be in one of a finite number of states.
Correct.
And then the next state of a cell is determined by its immediate neighbors.
Yes.
And that's it. And then the whole thing evolves in discrete time steps.
Exactly. So it's very simple, but as we've seen, you can get very complex behavior out of it.
Right. Okay, so Wolfram, he came up with this really interesting classification of one-dimensional CA.
Yeah, he classified them into 4 classes.
Okay. And why 4? Like, what's the big deal about those 4?
Well, he observed that, when you look at these one-dimensional CA, they tend to fall into one of these 4 categories.
Okay.
The first category, class 1, these rules tend to lead to very uniform states.
Mm.
So eventually all the cells settle into the same state.
Okay, so it's kind of boring.
It's kind of boring, yeah.
Okay.
Class 2 rules, these produce stable or repeating structures, so you get simple periodic patterns.
Okay. A little more interesting.
Yeah, a little more interesting, but still not that exciting.
Okay.
Class 3, Now, these are more interesting.
Okay.
These generate seemingly random, chaotic, non-periodic behavior.
Okay.
So, it looks like noise.
Okay. So is that like genuine randomness?
Well, it's deterministic, right? But it can be very hard to predict.
Okay.
But the really interesting class is class 4.
Right. Class 4, the cool stuff.
Yeah, so these are, they produce complex, localized structures that can move and interact in really interesting ways.
Okay, so more like lifelike, maybe.
Yeah, they're kind of in between order and chaos.
Okay.
Right? They're not totally predictable, but they're not totally random either. And it's this class 4 that Wolfram thought, and it turned out he was right, that were capable of universal computation.
Okay.
So this is Rule 110 is a famous example.
Okay.
And this rule, it's amazing because it's so simple, but it can compute anything.
Okay. So that kind of goes back to what you were saying before about how these systems, even though they're so simple, they can be just as powerful as, a supercomputer.
Yeah, exactly. And that has really profound implications for how we think about computation and also how we think about the world.
Right. Okay. And that brings us to this idea of edge of chaos.
Yeah, so edge of chaos is this idea that the most interesting things, the most complex phenomena, maybe even life itself, arise at this boundary between order and chaos.
Okay, so not too much order, not too much chaos.
Right.
Okay.
And this is where things get really interesting.
Okay.
So a guy named Chris Langton came up with a way to quantify this idea.
Okay.
He came up with something called the lambda parameter.
Lambda parameter.
Okay.
What's lambda?
So, for binary state CA, lambda is basically the probability that a cell will transition to the on state in the next time step.
Okay.
And Langton found that systems with a lambda value around 0.5 seemed to be poised at this edge of chaos.
Oh,
They were the ones that exhibited the most complex behavior.
okay, so like a sweet spot.
Exactly.
Okay, so 0.5, that's the magic number.
Well, it's not that simple. As with most things in science, the initial idea turned out to be too simple.
Okay.
Later research, for example, by Mitchell, Herber, and Crutchfield, showed that you could get really interesting computational phenomena at lambda values that were closer to the chaotic regime. So it's not just about finding the right lambda value. It's more complicated than that.
Okay, so the idea of edge of chaos is still good.
Yeah, it's still a really useful concept, but we have to be careful about how we apply it.
Okay.
It's not a simple formula. It's more about understanding the interplay between order and disorder in these complex systems.
Right. Okay. So let's talk about Conway's Game of Life.
Yes, let's do that.
Because you mentioned it earlier, and I think it's a really good example of a CA that shows all this complexity.
Yeah, so Conway's Game of Life is a two-dimensional CA.
Okay.
And it's got these really simple rules for how cells are born, how they survive, and how they die.
Right.
It's all based on the state of their 8 immediate neighbors.
Okay.
And, despite these simple rules, you get these incredibly complex patterns emerging.
Right. And I know that some of these patterns, they can actually move around.
Yeah, so there are things like gliders, which are these little patterns that move across the grid.
Okay.
And then there are things like eaters, which can, consume gliders.
Okay.
And people have even come up with names for all these different patterns. There's a whole zoology of Game of Life patterns.
That's pretty cool. But here's what's really mind-blowing.
What's that?
The Game of Life has been shown to be a universal Turing machine.
Exactly. That's the most amazing thing about it.
Yeah. So what that means is, given the right initial conditions, it can compute anything that a regular computer can compute.
That's right.
And that's wild.
It is, because it means that you can't predict what's going to happen in the Game of Life in general.
Okay.
Because of the halting problem.
Right. Okay. So we can't always tell if a program is going to stop or not.
Exactly.
And that applies to the Game of Life as well.
It does. So for some patterns, the only way to know what's going to happen is to actually run the simulation.
Okay. And that brings us to algorithmic irreducibility.
Yeah, so that's the idea that for some systems, the best way to figure out what's going to happen is just to simulate it.
Okay.
There's no shortcut.
Okay. And Illichinsky says that the Game of Life defines the most efficient simulation of its own behavior.
Yeah, so it's kind of like, the system is its own best model.
Okay. And that's got to have implications for how we think about the world, right?
It does, because it means that there might be some systems out there that are so complex that we can never fully understand them.
Wow. Okay. Now, you mentioned earlier that there are all these variations on CA.
Yeah, so we've been talking about the classic deterministic synchronous CA,
Okay.
but there are all sorts of other types of CA. There are probabilistic CA where the rules are not deterministic.
Okay.
There are asynchronous CA where the cells don't update all at the same time.
Okay.
There are non-homogeneous CA where different cells can have different rules.
Okay.
And there are even CA with continuous states.
Okay.
So there's this whole, universe of CA out there.
Wow. Okay. And what are some of the applications of these different types of CA?
Well, they're being used in all sorts of different fields.
Yeah.
So, for example, people are using them to study thermodynamics of computation,
Wow.
which is about understanding the energy costs of computation.
Okay.
They're also being used in AI, artificial intelligence, and also in genetic algorithms where you're trying to model, evolution.
Okay.
So they have a lot of potential applications.
Right. Okay. So now let's get back to the philosophy.
Okay, let's do that.
So the Stanford Encyclopedia, they talk about some of the key philosophical implications of CA.
Yeah.
And the first one is emergence.
Emergence. Yeah, that's a big one.
Right, because, CA are basically all about emergence.
They are.
You have these simple rules, and then, boom, complex behavior.
Exactly. So it's a great way to study emergence.
Okay. And philosophers, they like to distinguish between two kinds of emergence.
Yeah, there's epistemological emergence,
Okay.
and there's ontological emergence.
Okay. And what's the difference?
So epistemological emergence is about how we come to know about emergent phenomena.
Okay.
It's about the limits of our knowledge.
Okay.
So, for example, in a CA, we might have complete knowledge of the rules, but we still can't predict the global behavior.
Right.
So that's an example of epistemological emergence.
Okay. And then ontological emergence.
Ontological emergence is about whether these emergent properties are really real.
Okay. So not just like a product of our minds.
Exactly. So are they genuinely new things in the world?
Okay. That's a big question.
It is.
So CA, they've been really helpful in understanding the epistemological side of
Yeah.
emergence.
They have.
Because, as we've seen, even when we know all the rules, we can still be surprised by what happens.
Yeah. So that shows that there are limits to what we can know just by looking at the parts of a system.
Right. Okay. And Andy Clark, he came up with a way to characterize emergence.
Yeah, he talked about 4 aspects of emergence.
Okay.
Collective self-organization, unprogrammed functionality, interactive complexity, and incompressible unfolding.
Okay. A lot of big words there.
Yeah.
Can you unpack those a little bit?
Yeah, so collective self-organization is basically the idea that these emergent phenomena arise from the interactions of many simple components. And CA are a great example of that.
Right, because you've got all these cells interacting with each other.
Exactly.
Okay. And then unprogrammed functionality.
So unprogrammed functionality is the idea that a system can do things that it wasn't explicitly programmed to do.
Okay.
So again, CA are a good example of this.
Okay.
The rules of a CA don't say anything about, gliders or eaters, but those things emerge from the rules.
Right. Okay. And then interactive complexity.
Interactive complexity is just the idea that the complexity of a system comes from the interactions between its parts.
Okay.
And CA, again, are a good example of that.
Right.
Because the complexity of a CA comes from the interactions between the cells.
Okay. And then finally, incompressible unfolding.
So incompressible unfolding is the idea that the only way to figure out what's going to happen in a system is to actually run the simulation.
Okay. So no shortcuts.
No shortcuts.
Okay. And CA, they can be a good example of this, right?
Yeah, some CA are like that.
Okay. But not all of them.
Not all of them.
Okay.
So, for example, Crutchfield and Mitchell, they did some really interesting work on evolved CA.
Okay.
And they found that some of these CA could solve a particular problem called the classification problem.
Okay.
And the way they solved it was by developing these stable structures that could interact with each other.
Okay.
And these structures, they weren't explicitly programmed into the CA. They emerged from the evolution of the system.
Okay.
And what's really interesting is that Crutchfield argues that this is an example of intrinsic emergence.
Intrinsic emergence. Okay. What's that?
So intrinsic emergence is the idea that the emergent properties are not just in the eye of the beholder.
Okay.
They're really there in the system itself.
Okay. So it's not just that we're seeing pattern.
Right.
The patterns are really there.
Exactly.
Okay.
And he argues that, if emergence were just in the eye of the beholder, then you would have this infinite regress of observers.
Okay.
An observer observing an observer, and so on.
Right. Okay. So that's a problem.
It is.
Okay.
Yeah.
But going back to incompressible unfolding.
Yeah.
you said that some CA aren't like that.
Yeah, so for example, in the classification problem that Crutchfield and Mitchell were studying,
Okay.
they found that you could actually predict the outcome of the CA without having to run the full simulation
Okay.
because you could understand the behavior of these emergent structures.
Okay. So it's not incompressible.
Right.